So here's the answer to lecture 5's exercise. Recall this is the type signature of fold L and fold R. They are folds that the first argument is a function, the folding function for each. The second one is the starting value of the accumulator of type B. The third is your collection of A's, and the fourth is the final value of your accumulator after the end of the fold. Fold L starts from the left, so it goes from left to right across the list, and fold R goes right to left across the list. And fold map is sort of the more true canonical fold. It folds, you have a function that maps into a monoid, and then your collection of A's, and you get a monoidal value. So yeah, of course, sometimes you do want to fold L or fold R, like when your accumulator is in a non-monoidal type, or when you want to specify a non-conventional starting state of your accumulator. Anyway, you can implement fold L and fold R in terms of fold map, and the way you do it is with endo. So here we have fold R f z x's as a fold map. Recall that the endos are functions from A to A. That's what an endo of A is. You turn the x's in the list into endos on the accumulator type, and you'll sometimes see that I use, particularly with these field getters, with a lot of these wrapper types, I put the field's name in infix, and since it's just a function, that's fine. But it's equivalent to, this more parenthesis-heavy construction at the bottom. Fold L, one way to do it is to flip your F when you're building the endos. So you're still building up endos, but you're composing left to right. And to do it on the reversed list, because you have to do it on the reverse list. And it's not very different. Okay, so if you are using GHC 710, you'll notice that there's a more general type signature. Rather than fold map being on a list, it's on a foldable, which is a collection that you can fold across. List is foldable, but there are other things that could be foldable, so why restrict ourselves to lists? My point being that all of this stuff will still work. If you use 710, you'll just have slightly different type signatures. So then I asked, why does up top the fold map on any's, where the first any is true because 1 equals 1, and then you have an infinite list of falses, return immediately, while a fold L or false on that infinite collection, which is supposed to be semantically identical and would be if they were finite lists, never returns. And the answer there is that in the any monoid, we're able to stop computing due to laziness. The any is a Boolean brought into this type where we say true mappend anything is the true value in the any type. But when you do the fold L or the fold R, you have an infinite amount of work that you have to do first. And in that endo example, we would be composing an infinite number of functions together before we apply any of them. Now, the implementation I gave of fold L and fold R may not be the implementation that is actually there in the source code. I remember looking at it, it was a little bit different, but the principle is the same. Okay, so now we're going to climb Mount Monad. We're also going to learn about functor and applicative, and these are type classes that apply to parameterized types. And that's all that Monad really is. It's a type class. But the first thing we have to do in order to address this is to ask, is maybe a type? Certainly maybe int and maybe string and maybe int are all types. Is maybe a type? It's a type constructor. Does that mean it's not a type?
Class?
No, it's not a type class, actually.
It's an option or whatever the name of it is. Like,
Oh.
I don't know what the, like maybe it's a constructor in the union that is called whatever that union is called.
Okay, well, I'm gonna stop there and say that it's sometimes called a higher kinded type. With kind, type arrow type. The star is pronounced type. The kind system is the type system of the types. And maybe is not a concrete type. There's no value that's a maybe, as opposed to being like a maybe int or a maybe string. Of course, nothing is maybe a for any a, but it's not a maybe. It's a maybe a for some a. And as a type constructor, you can think of it as a function that maps types to types. So maybe maps int to maybe int, string to maybe string, maybe int to maybe int, and so on.
Can I ask you a basic question?
Yeah, sure.
Why is it not a type class?
A type class is we'll see a lot of type classes, but a type class is a collection of types that have similar properties. Or it's an interface in essence.
Yeah, okay.
And maybe, so for example, equality or eq is a type class because all sorts of different types can have equality defined on them, and they can have different kinds of equality, whereas maybe is just a constructor that maps one type into another type.
Doesn't it construct a type that conforms to the monad type class?
I'll get to that.
You can't derive a maybe. You can derive a type class?
Yeah, you can derive a type class. Well, the maybe type is, it will figure that out. Like the compiler will look at your code and usually be able to say, oh, just cat, that's a maybe of string. Now, if it sees a nothing, then it might not be able to figure out exactly what type it is. So, but yeah, a type constructor maps types to types, and hence we have the kind signature type arrow type. And yeah, that's exactly what the kind system is it's a type system for types, and it exists because we want our types to be well typed. So there you go. And if you want to see the kind of something, you can do that at the GHCI prompt with :k. So if you do :k int, you see that int is a type. If you do :k of maybe, it's type to type. And let's do something like either, or the function constructor, the arrow. Those both are two arity type constructors. They take two types and return a type. As for type classes, a type class is actually a higher kind of type as well. It takes a type and returns a constraint. And usually it'll be a free variable, or not a free variable, it'll be bound by the implicit for all, the variable that is affected by the type class. You can do fun things though, like if if you wanted to, you could say 5 is eq int fat arrow int, assuming that we have flexible contexts. And then if you apply it to something that's not eq, the type error, not because there's anything wrong with 5 being an int, but because eq int arrow int is not true. Like that's a constraint that it over constrains the system of equations. There's no solution. I just think that's kind of fun. So the good news is that our kind system is simpler than our type system. You know, the purpose of a type system is to be a simpler kind of computation that you use to reason about computation. And so the kind system should be even simpler than the type system, and it is. We have a base type called star, or type, and the arrow constructor. And the kind level arrow constructor has nothing to do with the arrow type constructor, which exists at the type level. So, you know, we'll often be dealing with the value level, the type level, and the kind level, kinds being the types of types. So a concrete type has kind star, or type, as you've seen. A one-argument type constructor like maybe is type arrow type. And either has kind type arrow type. And as we can at the value level, we have currying, or yeah, as we can do at the value level, we can curry. So either string has type arrow type as its kind, and either string int has kind star, which means that it's a concrete type. And just to point out a source of danger, the kind of arrow is type arrow type, which shouldn't be too surprising. But the one thing I want to point out is that the kind level arrows are a totally different thing from the type level arrow that lives in a function type. That is the kind of the function, or the type level constructor, which represents a function type, as in arrow A, B, or A arrow B, if you infix it, is the type of functions from A to B. Constraint is something that I showed. It's just another entity in the kind system that represents a type class instance. There are a few other kinds that you'll see that I'm not going to cover because they're way beyond the scope of what we're trying to do now. Oh, sorry. Okay. So yeah, as I showed, you can use :k to investigate kinds. And now we can talk about Functor, because Functor is a type class that applies to higher kind of types, such as basically meaning type constructors. Its kind is quantity type arrow constraint, or another way to think about that is that it's a type class on type constructors of arity 1. And Functor F has one member, fmap, which takes a function and an f of A and returns an f of B.
So this is a type class?
Yes.
That is a type class?
Yes.
Okay.
And if you go to lecture 5,
yeah.
The slides or the video, which I just put up on YouTube, that'll show you some simpler type classes.
Oh,
like
I'm behind.
Okay.
I'll send you this.
Okay. So then, you know, can we define int as a functor? Is there a functor instance for a concrete type int? The answer is no, because it doesn't kind check. It is an id. And fmap of f composed g of x is fmap f dot fmap g applied to x. Or another way of saying that is that fmap of f composed g is the composition of fmap f and fmap g. So it's a homomorphism from the space of functions. It's a homomorphism from the space of what you might think of as scalar functions to functions on that container. And I'll explain that a little better later on. Now, when you see an equal sign in a law like a functor law, it doesn't necessarily correspond to any equality method, which may not even exist for your type. What it is extensional value equality. So as you recall, when we talked about equality, there's object equality, which is the most sparse definition of equality. Things are only equal if they're the same object. Then there's value equality, which is that they're equal if they have the same value, and that's what eq instances are for. And extensional equality, we say that x and y are equal if and only if x equals y in their type, if they are in an equality type. And secondly, if you map them into an equality type, they're still extensionally equal. So one way of saying it is that there's no way to distinguish them, to tell them apart using the double equal value of a constructor. So you're saying they're equal if they're equal according to their type, and if there is no equality for that type, then you might still have mappings into a type that does have equality, and the values or the images under those mappings will be equal as well.
So, see, f is an arbitrary function for me to be here,
Yeah.
and you can't do funny stuff like return a random number because there's no IO. Like, can v be like IO?
Yes. Yes, it could. It could. And
but then you can't get equality because they're not equal under the
well, yeah. I mean, then
I see.
So that's one of the interesting debates in Haskell is whether IO can really be called a monad when the equality laws, because equality is not defined on IOs, it's sort of undefined. I mean, we would say that there are many ways to discuss.
Probably like jump over that just by saying that no IO is ever.
Yeah, that's what I meant.
Right.
Unless they reference the same. But no, I guess you can't even. Can't like.
Yeah. I mean,
well, you could do let x in, right?
Yeah, I don't know. We'll jump down that rabbit hole some other time. So maybe is a functor. If you fmap anything over nothing, you just get nothing. And if you fmap an f over just x, you get just f of x. So the interpretation there is that maybe is a 0 or 1 element container, and you're doing the same thing as you do when you map across a list. List is a functor. I think we all know how that's going to play out. Fmap is just map. So maps the empty list to itself, and it maps x cons x's to f of x cons fmap f x's. So then we ask about something more interesting, like arrow. And arrow itself, the function type constructor, we can't really call that a functor because it's a binary type constructor. It's got arity too. But for any type R, we can define arrow R as a functor. So what I mean is that arrow RA is a functor of A. And our fmap is composition. So if we have a function g, which takes r's to a's, and we have a function f, which takes a's to b's, then f composed g is going to take r's to g's, and the types check out.
To b's?
To b's, yeah, that's right. Did I say g's? There's no g's in this world. There's a function called g. But yeah, it's going to take r's to b's. And the interpretation there is that instead of being a list where you have positional numeric indexes, you think of arrow R as an R-indexed container. Either is a functor. We define either E as a functor where the lefts don't get mapped at all, so the F just gets ignored. But fmap f right V is right of f of V. And so what that means is that fmap will apply, if we think of either as a computation, it will apply f to the rights, but it'll leave the lefts alone, because the lefts could be in a different type. Pair A is a functor where f mapping f over it, over the pair, leaves the first element alone, and it applies the f to the second element. So you can think of that as a one-element B container with a one-element B container with an annotation of type A. And the annotation is never changed by f mapping. And finally, there's IO, which is also a functor. When we f map a function f across an IO-capable action, we get the action that we get a new action that takes the action that was passed in and returns f of that. So we're interpreting IO as some container, some magical device that produces an A. And when we f map an f over it, we have the same IO, but it's producing f of A's. So f mapping doesn't actually change the behavior of the function IO-wise. It just applies an f to the output.
So, but it also executes the output.
Yes, it executes the same output. So if I have an action A and a function f, then f map fa will have all of the same side effects as A and none more, but it will return f of A instead of A as its value. You can define functor on your own user-defined types. So here's a tree, and we fmap, we want fmap id to be id. So that means it has to map empty to itself. And if it's operating on empty, it can't look at the thing. So we get that fmap of anything empty equals empty. And if we have node LXR, then we fmap that f on the left and the right subtrees, and we apply f to the x. And this is actually the only definition that works. So functor is actually, it's not derivable without language extensions, but in most cases, there's only one sensible way to define functor on a type.
So this just applies f to all the terminal nodes.
Exactly.
Or no, I guess
to all the values.
all the values. I guess because every single, not just terminal nodes, because in this tree, like every node's gonna.
Every node has a value. So it applies f to every value, and it keeps the same exact structure.
So like, so a type class, in my mind, is most useful. Like typically, my purpose of implementing a type class would be to not just to like define the function that the type class requires me to define.
Interesting functions that are defined on top of functor.
Because like I could, can you? Okay, let's say you have like you have a type. You can just can you define like a without actually implementing. I'm using all the wrong words, but without actually like having. Can you define a method on a type without having to define a type class? Right, you can do that, right?
Define. I mean, you could have like you can have your type and you can define its own mapping.
Function with that type signature.
Yeah.
What you're talking about?
Yeah, exactly. So why would I instance function defining it?
Right. So because all the stuff that uses fmap and assumes it's an instance of functor, like under the hood, we'll just be able to reuse.
Oh,
this
yeah. So that's
application
my
of
question. It's just an
fmap.
agreement to the other
Yeah.
types that are expectors.
Exactly.
Okay.
Because sometimes like you'll find cases where people expect a functor. For example, this is something we're going to cover a bit later, but it's kind of cool. There's a function called Let me see if I can get it to show. So we actually get a lot of use out of this scary looking type signature when we deal with lenses.
Okay.
A lens is something that for all functors f can turn an A arrow FB into an S arrow FT. And that might seem totally ridiculous. Like what use would that be? And what it's actually good for is defining places in settable and gettable places in nested data structures in a functional way. That's very useful now. I'm just showing it because it'll come up again in the course, and you will understand that type signature and why it's important. That's called a rank 2 type. Don't worry about it for now. And mathematically, every monad should be a functor. In 7.8, you can define a monad that's not a functor, but you shouldn't. But in 7.10 and beyond, every monad is a functor. So
this might be a dumb question. For anything to map, for anything to be mapped over, does it have to be a functor?
no, to be f-mapped over, it has to be a functor. But I'll actually get to an example of something that's not a functor, but it has its own quirky definition of map. So I'll get to that, actually.
And are some things, so some things are just automatically, some types are automatically functors, right?
Well, some types, yeah, some types come with a functor implementation. And sometimes when you create them, you'll be like, oh, that's an obvious functor. So then the question is, does functor equal container? Is that what a functor is? And the answer is not exactly, because there are containers that aren't functors. So let's talk about sets. You could either use data.set, which is a tree-based set. I believe it's a binary search tree. Or data.hashset, or just the mathematical set concept. And the reasoning is the same, or there are reasons why set is not a functor. So let's first look at data.set. And as you can see, it doesn't have the right type signature to be a functor. Can anyone see why it has the wrong type signature?
Returns it.
I mean, if set is f, then it looks a lot like the functor fmap. But there's one thing that's different.
It requires it to be ordered.
Exactly, the type class constraint. Set.map requires an ordered type because it's a tree structure. And to put things into that tree, it has to know how they compare, so it doesn't work on arbitrary types. And a functor has to accept any A arrow B. It has to be able to fmap any. It has to be able to fmap into any type. So that's a clue. And we could look at hash set, and it requires ORed and hashable. I'm still not sure why it requires ORed. I mean, you could build a hash set that doesn't. But in this particular case, there are still constraints on it, which means that that functor, it's not a functor because it doesn't have a type agnostic map. And finally, let's just talk about the mathematical concept of set, where if you have a singleton x and a singleton y, and x equals y, then the union of them is the set x. That is, sets ignore duplicates. And so let's say that you have a new type y, which is a wrapper around an int, but we've decided to say that in that type, everything is equal to everything, which is not against the rules, as it turns out. It's weird. It's not the way ints work, but it's not illegal. Well, why does this break the functor rules? Does anyone have an intuition on how you can break the functor rules with that?
And you're losing something.
That's the right intuition. So what is the first functor rule?
Identity.
Right, fmap id equals id.
Oh, and it doesn't though.
In this case, it doesn't. Because y composed with uny, that is, if you y something and then you uny it, that's id. You know, you're taking an int, you're turning it into the y, then you're turning it back into the integer that it was. So that seems, so you would expect fmap of id on a set of ints to return the same set of ints, but if you fmap y, you get a set with one element. So fmap of uny composed with y is not the same thing as fmap uny composed with fmap y. So yeah, as it turns out, yeah, because you're putting it into a type that has broken equality syntax. So you can think of a functor as a structured and type agnostic container. It doesn't care what type it's storing, which is not set, because set is this unstructured type that depends on eq. It cares about how its type defines equality. And functions can act or fmap on it in a composable way. So fmap id equals id is saying that fmap lifts the identity to the identity, and fmap f.g equals fmap f.fmap g, the second law, says that it's composition preserving, which is what I mean when I talk about homomorphism. It takes the structure of functions, the compositional structure of functions on the A's is being, or on the base types, is being lifted into the same compositional structure on the F images of those types.
So like in if you're talking about, like if you were looking at it in terms of like lambda calculus, it's stating that, I don't know how I would say that in words, I could probably write it down, but like basically that all of the lambda abstractions are exactly the same, but just with
I don't follow. I mean, I don't know how all lambda abstractions would be the same.
all, not the same, but they're all composed exactly the same. You know what I mean? Like, oh, don't worry about it.
Yeah, I'm not following. We'll have to talk about this later. So if you want to crack fmap and really understand what it is, it helps if you put parens around the last two arguments, because what it really does is it lifts a function from what you might think of as the scalar level to the container level. It takes an A arrow B and it returns an FA arrow FB. And functors are the beginning of getting into the concept of computational context, which is the driving motivation behind Monad. There's nothing about the Monad type class that says you have to use it as a computational context, but as sort of an emergent property, it works really well as a way of formalizing what is state, what is computation. So if you look at some of the functors that we know about, maybe A is a computation that might fail, and if it fails, it doesn't give any information. It just says nothing, or return normally with an A. That's just. Either is a computation that might fail with a left in the type E, or it could return normally, that's right, with an A. Arrow RA is a computation depending on read-only state of type R. So there's state that's being passed in to your world, but your computations can't change it. They just depend on it. List is interesting. There are two ways to view it, both of which are identical for functor. Now, when we get into something called applicative, they diverge a little bit. But the first way is it's a partial function on the ints, and in fact, it's a partial function that is total on 0 to n for some n. But we'll just see it as a partial function, some kind of index collection. Or we can also see it as multiple value computation, which when I talk about non-determinism in this class, I'm actually talking about deterministic non-determinism, which will be evident in a second. Right now it sounds confusing, but it's the idea that if you have a function that can return multiple values, and then you feed it into a function that accepts one value, you can apply it with all those values and branch out. It'll become more clear when I talk about the list monad. Pair BA is a computation that produced a write-only state of type B. And finally, IO of A is an IO-capable action. It can do anything that the computer can do, and it produces an A. A little bit more interesting than functor is applicative. All applicatives are functors, but they have this additional thing, two additional properties. One is pure, which is a function that takes an A and creates an applicative. And it's sort of the zero effect applicative. It's like return in the monad or in the IO world. And then this guy, the star and angle brackets, I don't know what to verbally call that, so I'm just going to call that apply.
We call it Snowflake.
Sure, Snowflake, in honor of, I have a cat named Snowflake.
Perfect.
When I was a kid. So yeah, we'll call it a snowflake. Snowflake takes an A or a B in an F context and an FA. So it takes a function and a value in an F context, and it produces a return value in an F context. And it's more powerful than functor because it gives us things like the representation of pure computation, but it also lets us define function application within the F context. So you can think of pure as the effect-free computation, and function application being the fundamental combination of values in lambda calculus as in life. The snowflake is sort of the fundamental operator. So every applicative is a functor. Fmap fx can be defined as pure f snowflake x. And you'll often see the infix operator, a $ in angle brackets. We'll call that dollar flake or something. But it's an infix operator that's the same thing as fmap. It's just that it's used when you're working applicatively. So this expression, which I haven't told you what it is yet, but it's pure pair snowflake 1, 2, snowflake 3, 4 is the same thing as fmap pair 1, 2, snowflake 3, 4. Usually you'll have a pure value for your function and applicative arguments. So let's talk about the applicative list. Pure x is the one element list with x. And f's snowflake x's is going to concat map over the f's, a map of each f over the x's. So what it actually does is it takes all of the f's and all of the x's and it computes a Cartesian product. So what it's representing is what I'm talking about with this deterministic, non-deterministic computation, where you just compute all the possibilities. Does that make sense? Can everyone see why, that applicative with the cats and dogs has the value that it does? And if it's not clear, we can talk about it. I'm available I will be going on vacation next week, but Haskell questions I'll still get around within a day.
Is there? It's like, sorry. Is the way that you, because you're basically, is the way that you apply to lists like that? Those are two lists of functions.
Right. So we have two functions on the left.
Yeah.
And we have two values that go into those functions, and we do the Cartesian product.
Yeah.
So for each fx pair that exists, we include it in the list that we returned.
What I'm wondering is if that is that like logically the way that you should apply two lists to each other, like that because you're saying that a list isn't applicative, right?
There's another applicative that is built around lists called zip list.
Yeah.
That I might cover later.
Okay.
Zip list is zipping, so it's index by index.
Okay.
This one computes all the possibilities.
Okay. So
So
this
you-
is just a chosen way to implement
Right.
applying two lists.
Sure.
Okay.
Sure. Yeah. This does all the possibilities. You give it 10 functions and 10 values, it'll give you 100 returns. Maybe is also an applicative, and really just a maybe is just a list that can only have one element in it. It's 0 or 1 elements. But just f snowflake just x is just f of x. If you have a nothing, then you get a nothing. So it's computation that might fail, and a nothing just ends the whole thing.
What's the difference between using like a chain of snowflakes versus like an either? Just curious state about the error.
I'm sorry.
I guess like if you want to know, you said a computation that might fail, right?
Sure.
Yeah. So if you want to perform a chain of computations that might fail, but instead of forgetting,
Oh, you can use either as an
Fail.
applicative.
okay.
Yeah, I'm not going. This is not exhaustive, and I think, yeah. In fact, there we go. Either E is also an applicative. If you have writes, that is, you've had no failures, then you get a write of f of x. If either one is a left, meaning a failure, then you fail. And if both sides fail, it returns the first, which means that the f, the left side, is always evaluated before, because it takes precedence.
Can you do me a favor and just really, you said something earlier that was like a quick description of the main difference between an applicative and a functor. That was like what's the,
Applicative has pure,
okay.
and it has, well, let me actually show you the sort of core difference, and this will actually also make sense of monad. The other thing I wanted to say, which is kind of cool, is that before I get to this, even though we have semantically left E1, snowflake anything is left E1, that means if you have two lefts, F happens before, but that's semantically. You don't have to define time, and they could be evaluated in parallel. Like you could have this guy evaluated first, but it wouldn't matter because the definition says, okay, but in our computational context, the F computation happens first. Now the thing I wanted to show you is that, Functor's F, this will just be comments, but Functor has fmap A arrow B arrow F A arrow F B. And then applicative, this guy, is very similar. So Functor is like an applicative, but you can only map pure values, pure functions across it.
Okay.
And then monad, which we'll get to eventually, this is the reverse bind or the flip of the bind, is like this. And what that means is that monads can change the shape of the computation dynamically. So the A's in the MA can affect how the computation evolves. So I'll get more to that later on.
So you could still, if you had like a list of ethers and you did a right fold, you could still get thunk blow up.
List of ethers.
Right?
You
Like
mean
if
an
you
applicative list?
if you took parentheses snowflake like
Uh-huh.
as a two attic function
Uh-huh.
and pass that into the fold, right? You could get a thunk blow up if you passed it too many
Well, that's
ethers, right? Or too many of whatever has instance of applicative.
you would blow out your type checker before that because here's a slide I have that so the shape of an applicative computation will usually have one big function of some arity n, and then that's the number of snowflake terms that you can have after it. So if you were in a condition, so each snowflake reduces the arity by one, the currying. So a computation that would cause thunk blow up would also hurt the type checker because it would be a function with like millions of arguments. If thunk blow up is even a problem, which I have to think through. But
Yeah, no, maybe what I'm saying doesn't make sense because of like maybe there's no way to code that in the type signature.
yeah, well, you can blow up the type checker pretty easily. There are many ways of creating exponentially large types in a small amount of code. You have to be doing something degenerate to do it, but you know, I am a person known for doing degenerate things. So, if you have a monoid W, then pair W is an applicative, or you know, essentially values annotated with that monoid W. So the pure X is annotated with mempty, and if you have F and X in this context, so they each have a annotation WF and WX, you get the pair that M appends the WF and the WX, and it returns FX. So our example, we're saying, okay, I'm calling this 2 to the function, comma, the function 2 to the snowflake using 7 with 7, and of course string is a monoid because it's a list. So you get calling 2 to the using 7 and the value 128. So it's computation with a monoid log.
Is this common, like in practice, to use that for like
It's not
logging of
uncommon.
actions? Okay.
It's not uncommon to use it for sort of a explicitly threaded logging. If you're going to be generating terabytes of log data, well then you have to deal with I/O because you can't hold all that in memory. So applicative parsing. This is our parser type. It's a function that takes a string. Parser A is a function that takes a string, and it returns maybe, meaning it might fail a string pair, a pair of A and a string. And the string that it would return in the successful case is the part that it hasn't consumed. So pure A is the parser that doesn't do anything. Whatever string you pass it, it says, I'm just going to pass that along with the value A that you gave me. That's the pure parser. It doesn't do anything, no side effects. And P snowflake Q is the parser that first it applies P to the string that you give it. If it's a nothing, then the parsing failed and it's done. And if there's a something, a just, then it gets a function F. You can think of that as sort of the continuation, and an S prime. And then it takes the second parser, so it's combining parsers. It applies parser Q to S prime. If it gets a nothing, it says I failed, I'm done. Otherwise, if it gets an X and an S double prime, which is the final state of the string that is consumed, then it'll return just F of X, where F is that function that came back in the first parse. So it gets the F in the first parse, the X in the second parse, and it returns Fx, and S double prime is the part of the string that it has not yet consumed. In English, oh, I'm sorry.
Oh, it's just a super quick question that I think is why I didn't understand it earlier. Is applicative designed for teaching, or for basically like the blueprint for applying something of, whatever that type is, it is applicative to itself or to another instance of that type? Like, you define applicative so that you can apply an array to an array, or a parser to a parser, like, or combine maybe.
Sort of. I think what you're getting at is if you view computation as an intermediate state and a continuation on that intermediate state, the continuation is a function, you can call it f, and the intermediate state is x. And applicative says the applicative around x,
Which is the intermediate state.
no, is the side effects that you had, or I'm sorry. So the thing about applicative that's interesting is because the side effects happen left to right, the side effects on the continuation happen first, the continuation f, and then the side effects on the state that's going to happen itself.
Do you need a backslash after pure A equals?
Yes, I do. That's absolutely correct. Thank you for catching that. So yeah, in English, though, pure x is the parser that always succeeds, doesn't do anything, returns x. And then PQ,
And you both being parsers.
yeah, P is a parser that attempts P, and if it succeeds, it's going to return a function, A or B. That is, it's going to say, okay, here's the part of the computation that you need to do once you give me an A. And Q is a parser that returns an A, and if that succeeds, then you throw that A into the function returned by P. And since we don't usually think of parsers as returning functions, we usually think of them as returning objects, I'll elaborate. So first of all, recalling this law, that pure f snowflake x is just fmap fx, we can think of the fmap, the infix fmap, which is that $, as a way of taking this pure functional value into an applicative context. So for example, we have a data type called record, which takes an int, a string, and an int. We have an int parser and a string parser. Let's just assume they exist. I didn't write them. And now we have a pure function called record, which is that constructor. So it's a function that takes an int, or it takes an int, a string, an int, and returns a record. And it's pure. We fmap it into parseInt, and we get a parser that because of the currying, returns a string arrow, int, arrow, record. Then we snowflake that, it's got to be a better word, with the parse string, and we get an int, arrow, record in the applicative context. And then we snowflake that with parseInt, and we get a parser that just returns a record. So, in fact, there I show exactly what I described, so I wasted breath describing it verbally, but that's essentially how it works. You know, the pure record is the parser that returns, that purely returns a function that takes an int, a string, an int, and a record. And all of those side effects that will happen occur in the parseInt, the parse string, and then the next parseInt. And we've seen that applicative creates this notion of computational context. Now, this is a really tough concept. I mean, this takes a while to really absorb. Monad is a little bit more fluid. So in applicative computation, the form itself betrays this known substructure. For example, you could be snowflaking an f of A or a B and an f of A, and getting an f of B, or snowflaking f A arrow B arrow C with an f of a and then an f of c and returning an f of c. But you can't use the intermediate values to change the shape of the computation. You can't loop conditionally. There is a concept called alternative that allows you to introduce looping into applicatives. I'll cover that later, not in this class. But you can't loop conditionally. You can't look at the values that are returned from that context and say, oh, I'm going to do something different. You're pre-committed to a shape of the computation. So now we get to monad. The important ones are return and bind. That's what the double chevron equals is. The double chevron without the equals is like a bind, but it throws the A out. That's the only difference, and it will be automatically derived for you if you give it return and bind. And then there's this thing called fail, which is generally considered a mistake. I'll talk a little bit about why it's awful. Okay, return is the same concept as pure in the applicative. It takes a pure value of type A and it lifts it into the monadic context. And the familiar return in the IO is just a specialization of this. The actual type signature of return is not A arrow IO A. It's monad M fat arrow A arrow MA. And then we have bind. That's the composition operator for monads. So what it does is it uses the values produced by the computation X. X is of type MA, so those values are of type A, and it selects future computations using F, which is A arrow MB. And this is probably going to require some concrete examples, so there will be plenty. The double chevron, the sequencing that doesn't bind, can be derived from bind. It's just throwing the argument away. So you're saying, okay, A1 sequence with A2 with the argument thrown away. That means that you care about the side effects of A1, but you don't care about the value.
This only makes sense for the idle monad?
No, for any of them. All this stuff works for any monad.
But I guess you said you only use it for the side effect, right? But if you can only have side effects within the IO monad.
No. Side effects are defined by the monad.
Gotcha.
Every monad has its own definition of side effects. So maybe, for example, there's one side effect which is failing.
Okay, got it.
I quit, I return nothing. The state monad has explicit state. That's the S arrow A pair S. Yeah. So monad, sorry, maybe is a monad. Return is just, or return X equals just X. And you bind just X to any F. And that F is going to take a pure A and return a maybe of B. And you're just computing F of X. And then nothing binding to anything is nothing.
So is the constructor for the monad, like maybe being a constructor for that, right? Like the keyword or whatever.
Well, just is a constructor, a value constructor. Maybe is a type level constructor. Maybe does not exist at the value level, but maybe does exist at the type level as a type constructor. Yeah. So here are some exercises. Just look at it, tell me what you think it's going to compute. Yeah, that's correct. And the next one, I got to go for 1 second. Anyone? Nothing. Nothing. Anyone disagree? Good, that's correct. How about this guy?
Still nothing.
Still nothing. How about this guy?
Just 18.
Exactly. How about this one?
Nothing.
Nothing. Got just 18, I've got nothing. Why don't you guys argue?
The case match on the previous page is gonna match on nothing and return nothing.
Yeah, so if there was a value in, I'm sorry?
Nothing.
Okay, so yep. Giving the argument a label was a red herring because in fact that argument X is thrown out. And if there was a value, you get just 18, but since it's nothing, that means, if you think of it as the computation, that means the computation already failed, it terminated. So this function will actually never be run, it'll never be evaluated.
Oh wait, so nothing, how is nothing, how are we able to use nothing as an argument in the third example?
The third example,
Because it explicitly says that there's like an else nothing.
right, so the function, okay, so on the left side of the bind, you have a monadic value, an MA, and the right side is a function that takes an A, just a pure A, returns an MB, so it returns a monadic value. And because it's thing is.
Is that what's supposed to separate the bind, like the bind from the map? Like the fact that that context can like change?
Yes, because when you fmap, you can't add any side effects. You're fmapping.
I have also a super basic question. Is that
Sure.
Is that slash in front of the X? Is that like an unwrapping operator or something, or
That
what
is a lambda expression. It's an anonymous function.
Oh, that's all it is?
Yeah.
Oh, okay.
It's because it looks like a lambda.
It's
Yeah.
that way.
It's in the slides. I'm going on vacation next week, and then the week after that, I'm gonna.
Wait,
It's my fault.
Yeah, I can tell you about this earlier. Sorry.
in the last two examples, so you're saying that those are not monadic, right? That they're just, there's no side effect. That's,
No, in the first one.
I'm sorry.
Okay, so in the first one, we have a just 5, which, as it turns out, is a pure value in the maybe monad because the only side effect that's allowed in the maybe monad is to fail. And then we bind it into a function that says, it throws out whatever the value is, but it says I'm just returning 18. But in the bottom example, failed or already given up to anything, you get the failed computation. I'm
Okay,
just,
so in the third example, it's nothing, like it's not being used as the argument. It's
No.
considered a failed computation, so that's why it's not returning nothing because of the else,
right,
right?
exactly. The
Okay.
function on the right is never evaluated, or it's never run in the third computation. In the
Okay.
second it is, and that's why we get nothing with just 9, because it hasn't failed yet. Then it says, okay, 9 is not less than 5, so now I fail. That's what's happening in the second one. But in the third one, it's already failed, so that function never gets evaluated, gets run. Yep, of course. So this isn't a new theme that maybe is failure. We're saying nothing bind anything is nothing, and that allows computations to be aborted immediately. But often you'll use, say, either E or some other monad for computation for failure because you actually want to know why something failed. And maybe it's a good toy example, but it's not how you should actually structure your error handling. And by the way, error and exception handling in Haskell is a mess, which we'll get to in a later class. But for now, I'm just going to ignore that. We'll talk about list. This is the list monad. Return X is the one element list with X. And when we have x's and we bind it into an f, we're doing concat map. And so let's do this as an exercise, and then I'll talk about what it is conceptually. So what do you guys expect from this one? We have 1, 2, 3, and we're binding it into x to the one element list x squared. And remember that what concat map does is it maps the function and then it concats. So it has to take a function that produces lists. Unlike map, which produces one value, concat map, you give it a function that produces a list of values, and then you concat it all together.
So we get 1, 4, 9.
14?
It doesn't sum them. There's no sum.
So you're not concatenating.
You're not adding, you're just
Not
concatenating
adding,
the
okay,
lists.
Got it.
Is it 1, 4, 9?
Yeah. Anyone disagree? Probably not now. It's 149. Map is a special case of concat map where you're just returning one value. So how about this guy? 1, 2, 3 bind x to lambda x to, if even x, then the one element x list, and if it's odd, then the 0 element list. What do we expect there?
It's a list of 2.
The list containing 2.
Not just a list of, a
Yeah.
list of 2.
Right.
You have to be careful and use the word just.
Anyone disagree?
So it's when it actually because of the way bind works, it gets itself a list of each individual thing, applies the function, and then concats them back.
Exactly.
A list of 2 means a list of 2.
Exactly. So what I've shown you is that map is a subcase of concat map, and filter is a subcase of concat map. That's kind of cool. I think it's worth showing that map and filter are both subcases of this sort of fundamental list operation. Okay, so 1, 2, 3 bind x to replicate xx. What do you expect to get there? And
1, 2, 2, 3, 3, 3.
Exactly, because replicate n x is n copies of x.
Oh,
So that's what you get. And then this one is, I'm just going to give the answer. It's got 7 elements. We got a 4-element list. For everything that's not a t, we cons it onto ct, and for t we cons it onto ct, and for everything else we cons it onto aa and gt. So we get those 7 elements.
It's supposed to be like DNA.
Yeah, I don't know if they mean anything. Okay, so the deterministic non-determinism that I've talked about, the searching and branching, that's what the list monad is. So if you take the list of 1 to 100 and you bind it to the function that takes an x, that's an x from that first instance of the list, and sends it to 1 to 100 bind function that takes y. So now you have an x and a y that you've bound in these lambdas. And then your body is if x squared plus y squared equals 6409, you yield a pair xy, and otherwise you yield nothing, you fail. Then you get all the solutions of x squared plus y squared equals 6409.
So does the non-deterministic part here reference the fact that the compiler can choose how to, in what order to execute these things, but they will always come back in the same order?
So it's determined.
Or non-deterministic just refers to the fact that you can think of it as like set, like drawing from a set.
You can think of it as non-deterministic. It's taking non-determinism and taming it by having functions return multiple values. So it's really not non-deterministic at all. Which actually, there's a really interesting discussion about what the list type is and whether, what approach to take to it, which would be an interesting diversion, but probably won't cover that now. But
Can you write this as like do and then draw x from?
that's what I'm getting to next. So wouldn't we want something like list comprehensions for that? Well, we have list comprehensions. We do have list comprehensions independent of that, but we also have do notation. And that's what do notation is on the list monad. On the IO monad, it's sequencing and assignment of intermediate values, but on the list monad, it's list comprehensions. We have this thing called guard, which is actually part of, I think it's part of monad plus, which is fail done properly. But we're saying, okay, let's do x selected from 1 to 100, y selected from 1 to 100. Let's fail all the computations where x squared plus y squared isn't 64 on 9, and in the ones that remain, let's return x pair y.
So failure case in a bind, like when binding, or I guess when doing a list comprehension, is really just resulting in an empty list.
Exactly, exactly. So what guard does is guard true returns an empty list, or I'm sorry, guard true returns a list of one element, and that element is just unit, which means there's no information other than I succeeded. And guard false returns the empty list. And because list comprehensions are Cartesian products, as soon as there's an empty list, it's like, okay, I'm throwing this out. So in this particular case, you have a Cartesian product of 10,000 things, but then they get through this guard, and most of them just get thrown out.
So how would you define a guard on like a non-list monad? Is that like if you have a like the failure case for most monads, I'm assuming would not be an empty list. It would be
Sure.
some other representation of that monad.
So
Nothing.
let me actually look up the type signature of guard. Word control dot monad. Alternative. But I think monad plus is alternative. Is it? Yes, monad plus is alternative. Alternative means that it has a 0. So the 0 would be the empty list or the nothing in the list monad. Basically a terminal value. You know, when you get a 0, you're done.
So you provide that when you're creating a monad. You tell it what it like. How do you tell it what its failure?
Yes.
is?
Well, not all monads are alternative. So some monads are not. But
So you couldn't guard.
you can't guard in every monad.
Okay.
Yeah. A little behind schedule, but all right. So yeah, you could do the list comprehension, which is what's on the right. That, I believe, is translated into the version on the left, which it has the guard. I'm not sure, but I believe that that's what actually happens. And like I said, do notation, there's nothing magical about it. It's just syntactic sugar for nested binds. So you can use one or the other, whichever is preferable. But let's talk about do notation. There are essentially 3 cases to think about when you're deconstructing a do block. The first is where you have an assignment. You're saying do A gets. I've learned that gets is the proper pronunciation of the backward arrow. Do A gets MA, and then more is equivalent to MA bind lambda A to more. And then if you don't have an assignment, so you're doing action 1 and then more, that's the same thing, except you're throwing away the return of the action. So you're binding it to lambda. That blank just means throw out the argument. Or you could use the double chevron without the equals. And finally, when you see a long list of do operations, you can split the bottom into another do block and treat it as a binary do block. So this is how you translate do notation, and it will just become a list of nested binds, possibly very, very long, but it all works out, and it's pretty cool. So finally, I'm going to talk about the state monad. It has an explicit state, not side effects in your computer, but it is what it really is it's a wrapper, but I'm just going to treat it as what it's isomorphic to, which is a function that takes an S, that's your state type, returns an A and a new S. And note that the monad is state S for some type S, not state itself, because state is a 2-argument type constructor. The actual state monad is this guy. To understand that, you have to learn about the identity monad, which actually isn't really that hard to learn. It's just why it's interesting is something to learn. And monad transformers, don't worry about that yet. For now, if you want to put something in the actual state monad, it's a function S arrow AS, or S arrow pair of A and S. You can just use the function called state.
What's the purpose of the statement?
We'll get to that. Actually, let me answer that now. A state SA. So an IOA is an action that can do arbitrary stuff that the computer can do, and it returns an A. A state SA is a stateful action returning an A, but the only stateful capability it has is mutating that S. So you're saying, okay, there's some state S, and a state SA has access to that S to produce the A, and it also can alter that state S, but it's explicitly threaded in. So for example, we have a stack. We define push A as the stateful action that our state is a list of integers. The top of the stack is the head. Push A is the action that doesn't return anything, so it just returns unit, but it conses that A onto the stack. And then we have pop, which is a stateful action that if the state is the empty list, it returns nothing and doesn't update the state. State stays the empty list. And if the state is a cons of x and xr, it returns just x, and it changes the value of the state to xr. And so that has type signature state, list of int, maybe int, because the state is the stack. That's the stateful parameter that's being passed in. And maybe int is what it returns. So then we can combine these stateful actions. We say, okay, let's call doit push5 composed, or push5 bind, but it's the sequencing bind that throws away the return because the return is just a unit. Push 7 and then pop. And if you take that doit action and you run it on the state, which is the empty list, you get the updated state, which is a list with 5 on it. There's one thing that's been pushed on the stack and hasn't been popped. And you get the result of that pop, which is just 7. If you take the same action, do it on the initial state 1, 3, well then you push 5, so now your state is 5, 1, 3. You push 7, so now your state is 7, 5, 1, 3. And then you pop, you get just 7, which is what's returned, and the state is 5, 1, 3.
Run state a method, like that's something previously defined before the state monad.
Exactly.
The state on it.
Exactly. Run state is how you get the function, the stateful function, or the function out of the state monad. The function is actually pure. Its only side effects are on a value of this. Yeah. Its only side effects are on the explicitly threaded state of type S. You could, instead of having this wrapper, you could just say S arrow pair AS is a monad. And that's what I'm going to do. I'm going to use that definition of state just to make things terser. But that's not what the standard library uses, and you should know that. The standard library uses it uses a wrapper and it uses monad transformers. Do you have a question?
Yeah, so trying to rewrite this into Polish notation, can I say the arrow type class applied to S and that quantity applied to the comma type class applied to A?
Well, those aren't type classes. Those are parameterized types. But yeah, you could say...
Yeah, you could rewrite it, right, as same as AS.
Yeah.
I see.
Polish notation is basically just Lisp.
Yeah.
So the state monad is defined like so. Return x is the function and again, in the real state monad, there's a wrapper around it, a wrapper constructor. But in this case, it's the function that takes an s, returns that x without any effect on the state, and a1 meaning action 1, bind f, is the function that takes a state. First, it computes that action a1 on that state. It lets a be that first, it takes out the value a that it returns and takes out the new state, which is s prime, and then it applies f of a to that s prime. And that will return some other value. In the monadic sense, it'll return, if you recall the monad type signature, it will return a new state and the f of a, which is of type B. I didn't explain that well. I have a slide later on that explains this better. So if it's not clear, just bear with me. The state monad for every state type S has these particular functions. I call them elements. They shouldn't really be called elements. Get is the state that returns the state. State SS, it is the function that returns the state and doesn't change the state. Put is a function that returns, put is the function that ignores the old state and just sets the state to whatever you've put. This x should be s. And it returns a unit. So the value returned by a put is a unit. That is, there's no information content other than, hey, I did it. But whatever you've put is the new state. The old state is thrown out. And then we have modify, which takes an f. Again, like put, it returns a unit, but it applies that function f to the existing state. So the new state is going to be fs. And finally, we have modify prime, which is a strict version, so it avoids thunk buildup. Because if you recall, $bang is the function application that is strict in the argument. And if you're going to be making hundreds of thousands of modify calls, you're better off using modify prime and just saying, okay, I want these stateful updates to happen now, rather than building up a thunk and doing things later and possibly blowing up memory. Fail. Fail is a mistake. If you're working with a computation that might fail, I have it saying use monad plus or the alternative type class, but actually monad plus is a monad with alternative. So let me just take that out. But that's, monad plus is a monad that has some definition of failing. Some monads don't. In I/O, fail hard crashes. But in the list monad, it returns the empty list. And it's kind of weird. And the reason it's important to know this, the behavior of this strange method, is that when you pattern match in do notation, if your match fails, it's a call to fail, the fail method. So it actually is important to know this, because in the list monad, failure in a pattern match doesn't mean that that it hard crashes. It doesn't mean the computation goes to shit. It just means, okay, everything that doesn't match this pattern, I'm going to throw out. So now we can explain sort of what an I/O really is. IOA is real world, arrow A, real world, where real world is the state of the whole universe. So obviously we can't actually formalize it. We can't store it in our computer. And not only that, but we technically change it even in pure computations because we're generating heat. But let's just pretend that it's a thing. And what it gives us is it gives us the semantics of I/O. return x is the function that takes the world, returns x, and gives you the world as unchanged as reasonably possible, ignoring like the heat that's been generated and the increased entropy of the universe. And then act 1, that's an action bound to f, gives you another action, another IO, that first thing it does is it runs that act 1 on world, generates an intermediate world called new world, and an A. And then we say, okay, let's apply f of A. That's going to give us f of A is going to give us an IO of B. We apply it to the new world, and we get a B, and we get the final world. Now, the only thing about that that's important or realistic is that this semantics says, okay, action 1 definitely happens before f, because we don't have this new world that the B computation requires. We don't have this A until we've run action 1.
Doesn't this abstraction like only work if you define real world as the universe minus the region that's representing this code, right? Because if it can like, if a program can like actuate, like tell a sensor to go and screw up its own chip, then this won't be true.
So,
Technically.
yeah, the real world is just a token. It doesn't, I mean, you're not actually passing it around. This is a conceptual way to think about I/O. And there is actually a token that's given the name real world that's passed around for I/O semantics. I think the compiler throws it away when it optimizes, but it's just there to say, okay, when you sequence things in I/O, you can't parallelize them, unless you've said you can. So if you have a do block of 16 items, they're all going to happen in that order. Whereas a pure computation with 16 things, 16 computations spanning into one, they can happen in any order.
I only brought that up because it's like, this is a really useful abstraction, but there's a lot of people that spend time thinking about like how it fails if you wanted to write something that's capable of like arbitrarily thinking about itself, and you run into something called Loeb's theorem.
Sure. I don't know about Loeb's theorem, but I mean, I do know that like,
You also die if you blow yourself up.
that too. Yeah, I mean, this is more, it's almost more metaphorical, although there is a token called real world that is passed around, and the dependence on this token is what allows the compiler to say, okay, I can't interleave these IOs, I can't change the order around, because these aren't just computations, these are actions that people expect side effects from. Of course, a pure computation does, theoretically have side effects in that it could overheat the computer, but we'll just ignore that for now. All right, so are there any questions? That's the question, Kat.
I remember him.
Yeah, you would. So is this like a magnitude 8 mindfuck? Like, good.
I think like, the applications of a monad make a lot of sense, but and even a functor, I think, but like the applicative, I don't know. I think maybe just, you said we're gonna have some practical examples at some point, and I think that's really just clarifying.
Sure.
Probably, yeah, wait for that.
Applicative is, as a computational context, more featured or more powerful than monad, but more powerful than functor, but less so than monad. So
Isn't it just sort of different, like applying like something of the same type to something of the same type?
well, all monads are applicatives, and I can show you that because you can define. I mean, pure is just return, and then
What is like just 5? Like just 5? Sounded weird. But
well, no, you might have, you can't do that, but you could do something like, this is what you're looking for, right? Where because it has to be a function on the left-hand side.
oh, that explains the whole thing.
And the requirement of the requirement of the function on the left side is essentially saying, okay, I know how many arguments I'm taking.
So it just has to be, or in that case, it has to be a monad wrapping, or it has to be a function inside the monad.
Sort of, yeah. It has to know what the structure of applications will be. It has to know the shape of the computation in advance.
Oh, which is why it's not. It's why it's more limited compared to monad.
A monad, yeah.
Because you have to place it in that format to say whatever's inside of you.
Exactly. Exactly.
Is it nonsensical to take out the just in the first part? Like that doesn't apply in this case with the
Like
split
this?
operator? Other side. If you take out the just on the other side.
Well, then what you want to do is you have to lift it into the applicative context.
You do. Okay.
But there's
What happens if you don't?
a shorthand for lifting, which is this guy that I showed. And that is just the same thing. So that's the same thing as pure. And this dollar sign in the brackets is the exact same thing as fmap.
So your dollar is like you're starting your applicative sentence and then keep chaining it with snowflakes.
Exactly. Exactly. So parsing is a case where you use applicative a lot because like you know what the structure is. Like if you're parsing, say, a flat file, that's standard applicative. If you are parsing something that could have like many patterns, then you need something stronger, which is alternative.
I can't imagine using an applicative. I mean, I sort of can, but I can't imagine that I wouldn't use a monad. That I would instead opt.
Yeah, you'll probably use monads most of the time, but there are advantages to applicative.
It's really cool to see it built up that way.
Yeah.
It's a really cool way to build up to know, like, to seeing sort of complements.
Yeah. So one strength of applicatives over monads is that there's a composition factor. So if you have functor f and functor g, then compose fg, which is defined as, I need to get home soon, but yeah, but so let me just do like this guy. The composition is also a functor. That's also true of applicatives, but it's not true of monads. So you can't compose monads the way you can compose applicatives. There are some cases where you want to use the applicative functionality. Now keep in mind that like applicative it's more of an interface to a type than a type. So something could be a monad, but you might decide that you only want to use applicative functionality.
Do you just do that for free if you make it a monad, or do you have to do all free?
710, you will have every monad as an applicative and every applicative as a functor.
But I mean, like, is that by force? Like, you had to write functor applicative monad? Or
I'm not sure. Let me try. Let me. So there is a language extension that allows you to derive monad, but let's start with this is just like my own maybe.
Yeah. It'd be interesting if you could derive all of that functionality from that.
There are language extensions that do it.
Oh, you already said.
Props to that.
Yeah, I know, right? Like, whoever figured out how to derive. I mean, like, I guess if you did it the other way, it might not be as hard as it sounds good. You can build it.
Let me just see if I can get this to work.
If you build it, they will derive. There you go.
Oh, because it's.
All does it take to be able to read Haskell errors?
Oh, so it is going to require me to
Okay.
define applicative, and that's going to require me to define functor. Let me see if I can.
Just between you and me, that's not.
Functor. So you can definitely derive, and then you'd still have to do applicative, but you do pure. I don't think you'd have to define return because it can just say return is pure.
I mean, it's, yeah. I'm not smarter than the people who make Haskell, so I'm sure there's a reason.
But that was a serious question. Like, how did you go from the whatever the like pattern matching trace printed out to?
Oh, I just saw maybe, and I knew that it would, that for it to know about maybe, I had to use.
Maybe. I see.
I had to use maybe values like nothing, and I
Gotcha,
meant
gotcha,
f nothing. So, but yeah, I mean, you do get the type signatures over time. It takes a while.
Do you have anything running in production
We do,
using Haskell?
do.
Awesome.
we do, and we're gonna have a lot more over time. It's definitely an interest of ours. I mean, I don't want to impose Haskell on people who don't want to use it. So my original title for this class was consensual Haskell.
I've been doing some F# work, and the leap, the more I read about Haskell, even going from F# to Haskell is still, I thought it'd be like, oh, it's not too bad. There's still a lot.
You should try the mess that is Scala. Like, I think Scala is very interesting and creative. And for what it is, I think it was well accomplished. I mean, it's not that, like, the people who designed Scala are very intelligent. It's just that the JVM is such a fucking
I was
nightmare.
gonna say I don't mess with the JVM really. I mean, the .NET framework isn't much better, but you know.
Oh, it's better. It's better. It's not, maybe, I don't know if it's much better, but it doesn't have type erasure, which is the source of much pain in Scala. But no, Haskell it's not perfect, but it's, I think it's like the best general purpose production language, assuming that you can afford a garbage collector. If you can't afford a garbage collector, then you can't use Haskell.
Yeah, I mean we can.
It's really interesting how like you're talking about coming from F# to Haskell is a big leap. And in some ways it's the same from Rust to Haskell, but it's almost, I had no idea when I started writing Rust, but it's so, I mean, algebraic data types and monads are the only way to do almost everything you want. All the standard library functions, all the standard library functions return results, which is an either of the result of the function or an error, or their maybe types. I mean, traits in Rust are almost word for word type classes in Haskell, and it's really interesting. But I remember asking somebody why people use monads in Rust, but they don't use the names, the mathematical names for monad functions, right? Like why there is no bind function, but you sure as hell bind to monads. Like you just might call it map or whatever.
Flat map.
Yeah. So exactly, flat map is everywhere, and it's just, and the guy was like, because none of us are mathematicians. That was his only answer, and he was basically, we don't want to make people. Not that I care. I think this is great. He's like, we don't want to make people learn math, and maybe it's interesting. You can write Rust and have no idea what you're doing.
Okay, but I'm a category theory idiot. I don't know any significant category theory, and I can still be productive in Haskell.
Yeah.
I think that it gives you a motivation to learn category theory, which, let's be honest, I'm 32 years old. I'm married with 2 cats. Like, I probably wouldn't have if there wasn't like a cool language that's built based on it. But yeah, I've heard people say that like Monoid should be called appendable, but a lot of the Monoid instances are not appending. Like when you're summing things, you're losing information, and that's part of the design. And then if you take that route, you're calling functor mappable, which kind of misses the point because you can't really map across a function as in all the values.
Yeah.
But you can lazily do it with composition. And then if you call monoid flat mappable, you're totally lost because most of these monads have nothing to do with flat mapping.
Yeah.
unless you're in Scala, where like the word bind is scary, so you use flat map.
I think it'd be interesting to teach people this at the start. The first programming language you learn was Haskell.
There's
Yeah.
there's lots of experience with that. I'll send you the link on a guy that like trying to teach his 10-year-old son like Haskell this first
Oh
time.
yeah, he's probably smart as fuck then. Like, I mean, if he pulled it off, like as a 10-year-old, like it's fine. Like
You just illustrated with boxes, right? Like
the kid
it's
is
contained.
Well,
Oh, is
I
it
am-
is he really smart?
You're right. It's like
Thank you.
Obnoxiously
Yes.
late for
Okay,
dinner,
yeah.
so thank you for coming.
I'm
Yeah.
Going off the air.